Linear algebra is very useful for quantum mechanics. We've already used a lot of the notation and terminology of linear algebra when we say, for instance, that two wave functions are orthogonal to each other. But quantum mechanics puts its own spin on things. In part, for instance, because we're not dealing with, say, three-dimensional Cartesian coordinates. We're dealing with a complex vector space that describes the state of a physical system. So dealing with complex numbers and dealing with vector spaces in a more general way is very useful, especially as we move away from simply solving the Schrödinger equation, but to manipulating solutions to the Schrödinger equation to infer the properties of physical systems. So linear algebra will be useful in the coming chapters. To justify why this is useful, I'm going to make a couple of analogies. There are some things that we can say on the basis of vectors. We have vectors, A. We can make dot products between two vectors. We can express a vector A in, say, Cartesian coordinates, ax x hat plus ay y hat plus az z hat. We can also express some vector A in a different coordinate system. I'll call it a sub alpha, not x hat, excuse me, alpha hat plus a beta, beta hat plus a gamma, gamma hat. Where now the hatted vectors here are unit vectors, and the numbers ax, ay, az, a alpha, a beta, and a gamma are simply components. They're simply numbers. If these x, y, and z, alpha, beta, and gamma represent different coordinate systems, we can still say that this is the same geometrical object, A. The vector A is not changed by expressing it in different coordinate systems. It exists independent of any coordinate system. And of course, we can also take dot products of unit vectors with themselves and get 1. Quantum mechanically speaking, each of these expressions in terms of vectors has an analog. The vector A, that's what we've been talking about so far as, say, psi of x. That's the state of the physical system, the wave function. Taking the dot product of two vectors, that's our integral from minus infinity of, say, psi sub a star of x times psi sub b star of x integral dx. Expressing a vector in terms of one coordinate system versus in terms of another coordinate system is essentially the difference between looking at the state of the system as the wave function psi of x versus the wave function in momentum space, the wave function phi of k, which we got by taking Fourier transforms back when we considered the free particle. Finally, taking the dot product of a unit vector with itself is like saying the integral from minus infinity to infinity, back with our expression of the dot product, of psi star psi dx is equal to 1. That's our normalization condition. Essentially, the analogy between vector operations and the wave function, given these particular definitions of something like the dot product, is a good analogy, and in fact, it's a mathematical identity. You can think of, for instance, the dot product as adding up similar components, like the x component of A multiplied by the x component of B plus the product of the y components and the product of the z components. Looking at it in terms of the wave function, here we're taking the component of the wave function at some position x, multiplying it by the component of some other wave function at the same position, repeating that over all different positions, and adding up all of those different effective components, position components of the wave function. So there are analogies between linear algebra and quantum mechanics, and they actually end up being very useful. Quantum mechanics, as I mentioned, puts its own spin on things, and just for the sake of being able to use the actual notation that people who study quantum mechanics use, instead of writing a vector A with an arrow on top of it, we write it like this, with a line on the left and an angle bracket on the right. This helps us to distinguish what's a vector from what's a scalar. It also helps to distinguish us from what's been complex conjugated to what's not been complex conjugated. And just staring at this slide, this should not be psi b star. This should just be psi b. Apologies for the error. Keeping track of what's complex conjugated is obviously rather difficult because I've just made a mistake doing it. But keeping track of what's complex conjugated, we do with this notation by writing complex conjugated vectors essentially the opposite direction. Now, being somewhat punny, the physicists that invented this notation decided to call it bracket notation. And being physicists, they decided that this would be called bra and this would be called ket. So if you see something like this written, you should read it as either the vector A or ket A, whereas this would be read as bra A, or the vector A complex conjugated. You can think of these in terms of the wave function as this representing psi and this representing psi star, and we'll come back to what that notation means in the context of inner products in a few slides. But for now, this is the notation that I'm going to be using to represent vectors in quantum mechanics, where now the vector is a more general thing than just something in, say, three-dimensional Cartesian coordinates. We're talking about something even more general than the wave function. It represents the state of a physical system independent of any coordinate system. So it's not psi of x. It's the state of the system, which can be represented either by psi of x or phi of k or an infinite sum of stationary states to the solutions, stationary state solutions to the Schrödinger equation. They're all different representations of the same physical state, and that physical state is what we mean by writing something like ket A. So that's the overall analogy, and that's the notation. Just to very briefly review some of the basic properties of vectors, we have vector addition. We can say vector alpha plus vector beta is equal to some vector gamma, which of course is also equal to the vector beta plus the vector alpha. Addition is commutative, and addition of two vectors gives you another vector. We of course have a zero vector. If we take some vector alpha and we add the zero vector to it, we just get alpha back. We have scalar multiplication. I can write something like A times the vector alpha and get something which I'll call the vector gamma temporarily, where gamma is just some vector that essentially points in the same direction as A but is only slightly longer or shorter, having been scaled by A, hence the term scalar. This scalar multiplication is distributive. I can write some scalar A times vector alpha plus vector beta as alpha times vector A, sorry, getting my notation mixed up, A times vector alpha plus A times vector beta. Or alternatively, I can look at A plus B times some vector alpha as A times the vector alpha plus B times the vector alpha. So scalar multiplication distributes across addition versus of vectors and across addition of scalars. Scalar multiplication is also associative, of course. I can look at A, B times the vector alpha as either A times, pardon my notation, as either A times B vector alpha or B times A vector alpha, or as AB vector alpha. These are all equivalent. Scalar multiplication commutes and is associative. I already mentioned the additive identity here. There's a multiplicative identity as well. I can multiply a vector alpha by the scalar 1 and just get the vector alpha back. But those are our basic properties. Hopefully this is familiar. Either you can understand it from studies of linear algebra in general, or just by analogy with the day-to-day use of vectors in physics. Moving beyond the basic structure, one nice feature of vectors in linear algebra is that we can make linear combinations of them. For instance, if I have some vector A alpha plus scalar B vector beta plus scalar C vector gamma plus etc., I have a combination of vectors, each multiplied by scalars and all added together. This brings to mind a couple of useful concepts. First of all, linear independence. If I can write alpha is equal to, say, A times some vector beta plus C times some vector gamma, then you say this set, alpha, beta, and gamma, is not linearly independent. If, however, I cannot write alpha as a sum of beta and gamma multiplied by appropriate scalars. If there is no choice of alpha and A and C, such that I can make a sum of beta and gamma that equals alpha, then we have a linearly independent set. Alpha, beta, and gamma would be considered linearly independent, or alpha would be considered linearly independent of beta and gamma if it cannot be made by a linear combination of beta and gamma. If you have a bunch of vectors with which you can use to construct other vectors, you'll never get anything that's linearly independent from those vectors, but you can get vectors that are not in your original set. For instance, suppose I have some set of vectors xi. If I can write, let's say, my vector alpha as a sum ci xi, where I goes over the range of all of my vectors in this set, I've expressed alpha in terms of xi. In this case, I would say I have expressed alpha in the basis of states, or a basis of vectors given by xi. This ci here is, in some sense, c sub I is the x sub I component of the vector alpha. So if I have a set like this that I can use to express other vectors, you can describe that set as being a basis. Bases have other properties, and you can construct bases that have additional properties than this. Some bases are better than others, especially if you have a variety of purposes you want to accomplish. But the notion of a basis is that it is a set of vectors that can be used to construct other vectors. And the set of vectors that can be constructed from a basis, the space of vectors that can be constructed from a basis, is the space spanned by the basis. So, for instance, let me write, if every alpha in some space, the space that we're interested in, can be written like this: alpha equals sum over I c sub I times ket x sub I, we say the set of basis vectors x sub I spans the space we're interested in. For instance, the x, y, and z unit vectors in Cartesian three-dimensional coordinates spans all of three-dimensional space, three-dimensional Cartesian space. So if I have a set of basis vectors that spans a space, the dimension of the space is the minimum size of a basis. So if I have, say, in 2 dimensions, in the plane of this sheet of paper, if I have a vector that points in that direction, and a vector that points in that direction, and a vector that points in that direction, all in the plane of the screen here, I have 3 vectors, but they are not linearly independent, since I could construct this vector from a combination of these 2 vectors, or in any other order. Any of these vectors can be constructed by a superposition, by a linear combination of the other 2. And I have 3 vectors, so you would think I have a 3-dimensional space, but it's not the minimum size of the basis. I could say, drop this vector, just work with these 2, and still have a set of vectors that I could use to express any vector that lies in the plane of the monitor. So that's a little bit about superposition and linear combinations and some of the terminology that we'll use to describe what happens with them. The next major topic is inner products. The inner product in quantum mechanics, the inner product between 2 vectors is written like this. I'll keep using my Greek letters. Bra alpha ket beta. And you can think of this a little bit like A dot B, working with conventional vectors, but it's different. And it's different in a couple of ways. First of all, we're working with complex conjugates now. So if I wrote alpha beta, inner product, and I compared that with beta alpha, I would have to take the complex conjugate. If I exchange the order of the two vectors in an inner product in this complex number space, you have to take the complex conjugate of the result. We do have some familiar results, though. For instance, if I take alpha and dot it with itself, take the inner product of the vector alpha with the vector alpha, you get a real number, and it's going to be greater than or equal to 0. You also know, and this should hopefully not surprise you, that if alpha dotted with itself, the inner product of alpha with itself, equals 0, if and only if alpha is equal to the 0 vector. It's very common to write the 0 vector as just 0. It's usually reasonably clear from the context whether you're talking about a 0 vector or a 0 scalar. This is a little bit like writing 0 without units. We do that a lot in physics. We'll say, how tall, how long is this? Well, 0. You wouldn't say 0 meters or 0 nanometers or 0 kilometers because it doesn't matter what the unit is if it's 0. It doesn't really matter if we have vector 0 or scalar 0, it's still 0. We also have some familiar concepts. For instance, if I write alpha inner product with beta, and that equals 0, we say these two vectors, or states, are orthogonal. If we have a set of states, xi, such that xi dotted with, or inner product with, xj is equal to the Kronecker delta ij, we say we have an orthonormal set. This xi set is orthonormal. For instance, if I write x, y, z as unit vectors, they form an orthonormal basis for three-dimensional Cartesian coordinates. Now, note that in all of this, you might think, well, I'm taking the inner product between two vectors. I know how to do that. I figure out what the x components and the y components and the z components are. I multiply them together and I sum them up. But I want you to start divorcing in your mind the notion of something that looks like this from something that looks like this. Because we don't necessarily have components that we want to consider. We have physical states. And it turns out the mathematics of linear algebra can tell us about the properties of these states and how they interact without actually expressing them in any basis. Of course, we can do a lot of things when we do express them in a basis as well, but the vectors themselves can live without the basis. Having defined an inner product, it's also useful to define a norm, and this is occasionally written as, like, if I write two lines with an alpha in the middle of it. This is more or less defined to be alpha dot product with itself square rooted. Since the square root, or since the inner product of alpha with itself was defined to be a real number, positive real number, the square root of this is also a positive real number. This is our unit of, or our definition of length, if you want to think about it that way. And if we have some vector alpha with norm 1, we say it's normalized. It's a unit vector. A normalized state. Your normalized state is a slightly more useful term than saying it's a unit state. You don't hear unit state, though you would hear unit vector. You will also hear normalized vector. So normalized is sort of a more general term. Finally, now while I have said that vectors can live without the components, it is useful to express things in terms of components many times. So if I have a basis of unit vectors, an orthonormal basis set that spans the space that I'm interested in this case, three-dimensional space, I can write the vector alpha as alpha x times, keep wanting to write x hat, times the vector x plus, alpha y times the vector y plus alpha z times the vector z. Likewise, for some vector beta is beta x vector x plus beta y vector y plus beta z vector z. And I can write out things like the inner product alpha beta, and it looks pretty much the way you would expect. It looks like alpha x star beta x plus alpha y star beta y plus alpha z star beta z. You can also, of course, write the inner product of alpha with itself and get alpha x star alpha x plus alpha y star alpha y plus alpha z star alpha z, which you recognize as the squared magnitude of all of those components, all summed up together. Each of these components, incidentally, these alpha x, alpha y, alpha z, beta x, beta y, and beta z, can be found by taking inner products. Alpha x is defined more or less as x inner product with alpha. Likewise for alpha y, being defined as y, unit vector, unit bra, y, inner product with ket, alpha. And likewise for z. This is all in three-dimensional space, and we can actually work in higher dimensional spaces as well. Nothing here is really limited to 3 dimensions. If I have some set of orthonormal basis kets, x sub I can write the vector alpha as the sum over I of some alpha sub I times x sub I, given suitable definitions for alpha sub I. In particular, alpha sub I is x sub I inner product with the vector alpha. And you can write out expressions for alpha inner product with beta. That's a sum over I of alpha sub I star beta sub I, or the inner product of alpha sub I with itself. Not alpha sub I. The inner product of vector alpha with itself is the sum over I of alpha sub I star alpha sub I. Total sum of all of the squared moduluses, whatever, of all of the components of alpha expressed in this basis. So that's a little bit about how linear algebra is expressed and some of the things that we can do with it. As an example, I would like to check your understanding with the Schwarz inequality. This is just an exercise in manipulating vectors, but the Schwarz inequality, and this is something that can be useful in quantum mechanics, what it states is that the inner product of some vector A with some vector B, squared magnitude, is always going to be less than or equal to the squared magnitude of A multiplied by the squared magnitude of B. So, inner product of A and B, squared magnitude, is always less than the inner product of A with itself and the inner product of B with itself. This is the squared norm of A and the squared norm of B. So your task is to check that this inequality holds for the two vectors given, where here x, y, and z is an orthonormal set that spans some three-dimensional space of interest. Note that I'm not necessarily talking about three-dimensional Cartesian space here, but it's a good analogy to keep in the back of your mind if you're having trouble imagining what these things should look like. Our whirlwind tour of linear algebra continues with linear transformations. Here, we'll write linear transformations with hats. For instance, T with a hat, capital letters especially, will be considered to be transformations. A linear transformation, quite simply, is a transformation that's linear. What it means for something to be linear is if I apply the transformation to A times the vector alpha plus B times the vector beta, I get A times the transformation T applied to the vector alpha plus B times T applied to the vector beta. If this sort of identity holds, the transformation you're working with is linear. It's difficult to work with transformations in general, so it's useful to consider what a transformation looks like if we have a vector in a particular basis. So suppose I have a set of basis vectors, x sub I. I'm not telling you how big this set of basis vectors is, but if we have our transformation applied to the basis vector x sub I, let's say x sub 1 in particular, that transformation applied to a basis vector will be given by another vector, which is in general going to be expressed as a sum of basis vectors. So x1 will be transformed into some number, which I'll write as t11 x1, vector x1, not xi, excuse me, tx1, plus some other number, t21 times the vector x2, plus t31 times the vector x3, etc., up to xn. If I have, say, x2, I get a similar expression, except I'm going to number things slightly differently. I'll say this is the t12 number, is the x1 component of the transformation applied to x2, plus, etc., t22 x2 plus t32 x3 plus, etc. So if I have some vector then, alpha, being expressed as a1 x1 plus a2 x2 plus a3 x3 plus, etc., up to xn, I can write that as a sum over, say, j equals 1 to n of aj times x sub j. And you can find these components, a sub j, the way we described in the last lecture. If I apply this transformation t hat to this vector alpha, I'm going to get a sum of sums. Essentially, the first thing that I'll get is this sum over j of aj, and then the transformation t hat applied to x sub j. But I know what the transformation t hat applied to x sub j looks like. It's going to look something like this. It's going to look like a sum over something I'll call I. But first I have my sum over j, then I have a sum over I, and I'm left with the aj as before. And then these sums, if I'm expressing them as sums, I'll end up with tij times x sub I. So this is just taking these summation expressions and substituting them in for the application of the operator of the transformation t hat to x sub j. You can exchange the order of summations here if you want to find out what the xith component is more straightforwardly. We'll do the sum over I first then, and then we have the sum over j of aj tij gives us the x sub ith component of the operator, the transformation t, applied to the vector alpha. I keep saying operator accidentally here. The connection with hat notation between our operators, for instance, p hat in quantum mechanics, and the transformations I'm working with here, t hat, is not coincidental. We will see there's a connection in the linear algebra interpretation of quantum mechanics between operators and transformations. So what we've done here is we've expressed our transformation t hat in a basis, x sub I, with, say, n entries. So we have some n-dimensional space with n basis vectors, and we can express our operator, our transformation, in that basis. What we get is these numbers, t21, t11, etc. It's convenient to represent these numbers as a matrix, instead of just writing out t11, t12, etc. We can take our t hat, our transformation, and in a basis, we end up with numbers, tij. And it's useful to write those tij's in matrix form. Upper left we have t11, then t12, up to t1n. Second row we have t21, t22, up to t2n, going all the way down to tn1, and all the way over to tnn. So that's the structure, and that's how we write these things as matrices. The ijth component here, incidentally, can be found by consideration of the orthogonality of our basis vectors. tij can be written as x sub I inner product with t, the operator, acting on the basis vector x sub j. So if I apply t to x sub j, we had expressions for that on the previous slide. We got a sum of the x sub j's running from 1 to n. And if we take the inner product using the orthogonality of the x sub I and x sub j basis vectors, we can pull out just the x sub ith component. And that will tell us what the number Tij is. So if we have some way of acting with these operators, you have an effective way of finding what the components of your operator are, of your transformation, in the particular basis that you're working with, x sub I. So, in this matrix interpretation, the sums that we expressed on the previous page have a nice interpretation. If I apply the transformation t to the vector alpha, I can write that as, and I'm going to cheat and just copy paste this matrix acting on the vector alpha. If I express alpha in this basis, I could write alpha as alpha 1, alpha 2, up to alpha n as a column vector. And the sums that we expressed on the previous page are exactly the matrix vector product. So treating the vector in our basis as a column matrix, we can do this matrix vector product, this matrix product. And what you end up with is the representation of t hat acting on A in this basis. So these matrix vector products will be a useful way of manipulating vectors and matrices as they represent transformations and states in quantum mechanics. This transformations, of course, can also be combined with each other. You can have a transformation A hat and add a transformation B hat. This, if you imagine applying it to a vector, say alpha, is just going to give you A hat applied to alpha plus B hat applied to alpha. And if you're working with matrices, the A hat plus B hat represented as a matrix, if I want to know the ijth entry of the matrix that represents the sum of these two transformations, it's just going to be A ij plus B ij. The element by element sum of the two matrices treated separately. We can also write out the product of two transformations. For instance, if I have A hat, B hat acting on the vector alpha, you can think about this as the composition, A hat acting on B hat acting on alpha. But it turns out that in matrix representation, this is just the matrix vector matrix product. You can work out all of the sums necessary to figure out what this sort of expression actually looks like in terms of components, and what you get is the summation expression for the matrix product. So we can compose transformations applying one after the other by multiplying their matrices together, and we can apply a sum of two transformations by simply adding the elements of their matrices. So we're going to be working with matrices quite a lot. It helps to know some of the things that we can do with matrices. What are their properties? Well, some things that we can do with matrices. We can take the transpose. The transpose of a matrix, denoted by putting a twiddle over the top of the matrix. If I have some matrix Aij that I want to transpose, that is the ijth entry of the transpose of A is Aj, exchanging the order of the indices in our matrix. Essentially, this means taking an entry below the diagonal and swapping it for the identical entry above the diagonal, flipping the matrix across the diagonal. We say a matrix is symmetric if the transpose of the matrix is equal to the matrix. Essentially, taking the transpose does nothing. And we say a matrix is antisymmetric if taking the transpose gives you the matrix back with a minus sign, if taking the transpose flips the sign. Essentially, if all the entries above the diagonal are the same as the entries below the diagonal, but with a minus sign. We can also take the complex conjugate of a matrix, which we'll write as A star, using our complex conjugate notation, and That's relatively straightforward. If I have some matrix A star and I want to know the ijth component, it's just Aij complex conjugated. Let me simplify my notation a little bit. If I have A star and I want to know the ijth entry, I have the complex conjugate of the ijth entry of A. It didn't really matter how I wrote that. To take the complex conjugate of a matrix, you take the complex conjugate of all the elements of the matrix. We describe then a matrix as real if the complex conjugate of the matrix is equal to the matrix, and imaginary if the complex conjugate of the matrix is equal to minus the matrix. If all the elements are real, you have a real matrix. If all the elements are imaginary, you have an imaginary matrix. Where things start to get interesting now is defining combinations of these operators. The Hermitian conjugate which is also sometimes called the adjoint of a matrix. And the notation here is A dagger. The daggers look much nicer in LaTeX, but this sort of A cross would be read as A dagger. And the Hermitian conjugate, A dagger, is defined to be the complex conjugate transpose of the matrix. Hermitian conjugates have an interpretation in terms of transformations and operators, which we'll come back to. But for now, we describe a matrix as Hermitian if the A dagger is equal to A. The Hermitian conjugate of the matrix is equal to the matrix. Or anti-Hermitian if the Hermitian conjugate is equal to minus the matrix. Coming back to our inner product, if we're representing states as vectors, if I have something like alpha, beta, the inner product, alpha, beta, I mentioned now that the alpha written as a bra as opposed to beta, which is written as a ket. The difference between bras and kets here is has something to do with the complex conjugate. If we're writing alpha and beta in a basis as vectors, the matrix product here, which is what we're working with, the dot product of the two vectors, can be written as alpha dagger as a matrix times beta. So alpha dagger, and I didn't really make that look like a dagger. To distinguish it from star, I need to elongate things a little bit. Alpha dagger times beta. The vector representation of alpha in a basis is, as it was in the previous page, a column matrix. Alpha dagger, then, the complex conjugate transpose, is going to be a row matrix. Beta, again, not being Hermitian conjugated, is going to be a column matrix. And I can take a row matrix and multiply it by a column matrix, and I'm just going to get a matrix with only one entry in it, a scalar, essentially. So that's how these sorts of properties work out. Transposing matrices, we'll talk about the symmetry of matrices, we'll talk about the Hermitian conjugates of matrices, Hermitian matrices versus anti-Hermitian matrices, and to close the loop a little bit back to what we talked about with inner products, Hermitian conjugates are what you need to convert your column matrix representation into a row matrix complex conjugate representation to actually end up with a sensible inner product of matrices in this complex number space. That's not all, though. We've got more matrix properties to work with. Back when we were talking about operators in quantum mechanics, we defined something called the commutator. We can define commutators in terms of matrices as well. And if I have some matrix A, the commutator with A with some matrix B is same as it was in operators, AB minus BA. Except now we're talking about the matrix product AB subtracting the matrix product BA. Matrix products are non-commutative, same as operators are non-commutative in quantum mechanics, and the connections are starting to become a little more clear. We can take the transpose of a product, AB, and if I have AB, the product, transposed, that's equal to B transposed times A transposed. So the transpose of the product is the product of the transposes, but in the opposite order. This follows over to Hermitian conjugates as well. If I have a matrix product AB that I want to take the Hermitian conjugate of, I get the Hermitian conjugate of B multiplied by the Hermitian conjugate of A. Just for the sake of clarifying notation, we also have a unit matrix, which is a matrix with 1s down the main diagonal and 0s off the main diagonal. For instance, if I wanted to know the ijth entry of my identity matrix, it's the Kronecker delta, which we learned about earlier when we were talking about orthogonality. That's still not it. There are still more matrix properties. Things to mention that you need to remember. The inverse of a matrix, denoted a to the minus 1, is defined such that a to the minus 1 times a is equal to a times a to the minus 1 is equal to my identity matrix. If you can find an inverse like this, these products work out. There isn't always an inverse. You have an inverse if and only if the determinant of your matrix is non-zero. So you need to remember determinants, which I'll just write as det of A. Your determinant of A is not equal to 0. This inverse also behaves a little bit like the Hermitian conjugate in the transpose, in the sense that if I have some matrix AB inverse, it's the inverse of B times the inverse of A, which you can see pretty easily by thinking about what would it mean to take the inverse of AB. Well, I would have AB times its inverse has to give me the identity, and you have to reverse the order in order to make that happen, because then I could identify B times B inverse as the identity. Pull that out, essentially, since it's going to do nothing if it's sandwiched between two other matrices. And then A times A inverse would also give me the identity, and I'd just be left with the identity. One last property to mention, I think that's about it, yeah. Unitarity. We describe a matrix as unitary if the Hermitian conjugate of the matrix is the inverse of the matrix. So I can take this little horizontal line and push it a little bit to the left. No. Notationally speaking, there is a lot of things to keep track of here. We have a dagger, we have a star, we have a twiddle, we have a minus 1. We have the determinant of A. And they all interact in ways that you need to keep straight. But unitary matrices will play a special role in quantum mechanics. The last thing I want to mention in this lecture about transformations and matrices is how to change the basis of a matrix. So suppose I have some matrix A. That's if I'm going to express some operator A in a basis, let's say basis 1, I'll get the matrix A. If I want to express it in basis 2, I'll get some other matrix, which I'll write, say, A prime. Actually, no. Let's call it B. So B is the matrix that represents the transformation A hat, but in a different basis. If you want to think in 3 dimensions, for example, the transformation A maybe multiplies your x-coordinate by 2. Well, multiplying the x-coordinate by 2 in one basis is going to be different because, for instance, you could have another basis where the y-coordinate was the x-coordinate, and then it would have to multiply the y-coordinate by 2. So your matrix representation would be different. You can think about changing from basis 1 to basis 2. That's going to be yet another transformation. So say I have some transformation that goes from basis 1 to basis 2. That transformation I'm going to call S. So if S takes a vector from basis A, a vector expressed in basis 1, and re-expresses it in basis 2, I can use S to figure out what B is in terms of A. So the first thing you're going to have to acknowledge here is that A acts in basis 1. And if I want an expression for something acting in basis 2, I'm going to have to take my vector from basis 2 back to basis 1, allow A to act on it in basis 1, and then convert back to basis 2. And the way we write that is S times A inverse times, S times A times S inverse. If I'm allowing this to act on some vector alpha, I can think about S inverse as going from basis 2 to basis 1. So alpha in basis 2, this S inverse alpha is going to be alpha in basis 1. Now that alpha is expressed in basis 1, I can allow A to act on it. That will give me another vector also expressed in the basis where A operates, basis 1. Then I can use S to transform back to basis 2. So if I have a vector in basis 2, I can convert it to basis 1, allow A to act, and then transform back. Now we know how to compose products, or how to compose operators or transformations like this. This matrix is going to be our matrix B, our representation of the operator A in basis 2. So this is how change of basis works. If I have some transformation S that I can use to connect basis 1 to basis 2 and vice versa, then I can take a vector expressed in basis 2, express it in basis 1, allow A to act, and then transform back to basis 2. And if I just treat all three of those operations as matrices, you end up with a matrix product that gives you the representation B, which tells you how A acts in basis 2. So essentially B is equal to S times A, I know I keep writing an inverse there, times S inverse, for some S that connects the two bases together. So that's about it for matrices. To check your understanding, given this matrix and this vector, calculate these quantities. The Hermitian conjugate of A applied to B, and then the Hermitian conjugate of B left multiplied by the matrix A. And the final question is to figure out how X and Y are related to each other. So just to get you back in the swing of doing matrix operations and figuring out how matrix vector products work. This is the last major piece of our discussion of linear algebra, eigenvalues and eigenvectors. This is one of the really important pieces from the perspective of quantum mechanics. Over the past lectures, I've probably said eigenvalue or eigenvector or eigenstate without really thinking about it or noticing. So it's important to understand what these things are, and they will be used extensively throughout our discussion of the mathematical formalism of quantum mechanics. Essentially, what eigenvectors and eigenvalues are special vectors for a transformation. Suppose, for example, I have Cartesian 3-space, say x-coordinate, y-coordinate, z-coordinate, x-axis, y-axis, and z-axis. If I consider a transformation that is rotation about the z-axis, for instance, a vector here in the x, y plane would be rotated around, say, to point in some other direction, remaining in the xy plane. A vector that points along the z-axis would remain unchanged, whether it's pointing upwards or downwards. These vectors that are unchanged in a transformation have some special status, and it's not simply, for instance, the vector that points along the z-axis in a transformation like a rotation like this. You can think, for instance, suppose I have just 2 dimensions now, and consider a transformation that takes like a box shape like this and maps it to something that's skewed, stretched out in the x direction and smooshed over in the y direction. If I had a transformation like this, you can probably imagine what one of the vectors that remains unchanged would be. It points along the x-axis. And it's not going to remain unchanged, but it's going to be extended slightly. It's going to point in the same direction. As opposed to some other vector, which for instance points in, say, this direction, and it's going to be extended and shifted over. So The blue vector here is not unchanged. The orange vector, however, is essentially unchanged. It points in the same direction. There's actually another vector in this transformation that remains unchanged, and it points sort of off in this direction. That vector actually legitimately remains unchanged. It is neither extended nor contracted. You can think about this transformation as taking your x-coordinate and multiplying it by some value. The y-coordinate remains unchanged, but the x-coordinate also depends on the y value. The higher up you go, the further over you get shifted. And if you're lying along this vector, the fact that you get shifted over in x and the fact that you're along a line, you're essentially along a line where the amount that you have moved up in y counteracts the amount that you're shifted over in x, and you end up essentially back where you started. So these special vectors are called eigenvectors, from the German prefix Eigen, which means self or proper. So these are the self values or the proper values of a transformation, the values that return to themselves in some sense. And the amount, for instance, by which this orange vector gets increased in length or decreased in length is the eigenvalue. More formally, what we're looking at are equations that involve transformations. So, as before, t hat will represent my transformation, and I will write vectors associated with the space that we are interested in as cats in bracket notation. Your eigenvalue equation fundamentally then is your operator acting on your vector gives you some eigenvalue, lambda, times your original vector. So the action of your transformation is to return a scaled version of the vector that you started with. Since most of what we're going to be talking about in this lecture is what happens when we represent a transformation in a particular basis, you can think in terms of matrices. The matrix T acting on the vector A gives you back the eigenvalue lambda times the vector A. And we can rewrite this a little bit if you think about trying to bring the right-hand side over to the left-hand side. You would end up with T acting on A minus lambda multiplying A, lambda just being a scalar, not a matrix or a vector or anything. And if I want to factor A out of this expression, I can write this as the matrix T minus lambda times the identity matrix, all acting on A as a matrix. So this is going to be equal to 0, as is this. And this is the sort of equation that we're going to be considering when we talk about finding eigenvalues. So lambda is our eigenvalue, and A is our eigenvector. I haven't said why these things are interesting yet. Mostly they're interesting because they tell you what the core properties of the transformation are. These are sort of the most interesting facets of a transformation. And when it comes to quantum mechanics, we'll see that these things are actually very important. So bear with me while we go through some of the mathematical details. If what you're interested in doing is finding eigenvalues, the easiest way to think of it is in terms of that expression. We're working with a matrix equation, T minus lambda times the identity, multiplied by some vector, is equal to 0. You can imagine trying to solve this by standard techniques involving matrices. For instance, if I called this matrix A, I would have capital A acting on A is equal to 0. And I could solve this by left multiplying by the inverse of A. I can multiply by inverse of A over here, and by inverse of A over here. The right-hand side, of course, is going to remain 0. The matrix A, no matter what it is, acting on the 0 vector, will give me 0. But on the right-hand side, I'll end up with the identity here, and I'll just end up with A equals 0. This was not particularly informative. It didn't tell us anything about A. The reason that we can have these vectors that are unchanged by transformations is that it's actually impossible to solve the equation like this. This doesn't work. And the reason this doesn't work is that if we have A not equal to 0, the only way this equation can have a solution is if the determinant of T minus lambda identity is equal to 0. So our actual equation to determine the existence and value of an eigenvalue is this equation. That's what we're interested in. The determinant of the matrix T minus lambda times the identity equals 0. This is an equation that we can solve for lambda. And if we solve it for lambda, we'll find the eigenvalues. We won't find just one solution to this equation. We'll find many solutions. If this is an n by n matrix, this equation is an nth order polynomial in lambda. So if we have an nth order polynomial, we're working with complex numbers, we have n roots, so we have n eigenvalues. These eigenvalues are not necessarily distinct, but we should have n of them. So whatever the dimension of our space is, whatever the size of our matrix is, we should get that many eigenvalues. So the best way to see how solving this process actually works is to go through an example. So find the eigenvalues of this matrix, 1 minus I minus 1. There's some special structure to this matrix. If you recall back to when we were talking about the properties of matrices, if I take the transpose of this matrix and the complex conjugate, I find that I have my original matrix back. The I and minus I will exchange places, but then I will be exchanged for minus I again when I take the complex conjugate. So this is in fact a Hermitian matrix, and Hermitian matrices have some nice properties from their eigenvalues that we'll talk about more later. But for now, let's figure out what finding the eigenvalues actually looks like. We're looking for an equation of the form matrix A multiplied by some vector, and I'll just leave it as vector A, equals lambda times our vector A. And I told you that you could solve this by moving this over to the left-hand side and trying to solve for the determinant of your matrix under those circumstances being equal to 0. That's what's called the characteristic polynomial, the equation, the characteristic equation. The determinant of 1 minus lambda minus I minus 1 minus lambda is equal to 0. That's our characteristic equation. That's what we get when we rewrite this as A minus lambda times the identity matrix multiplied by A equals 0. And this matrix is what we're taking the determinant of. So you know how to find the determinant of a 2 by 2 matrix. It's just something that you can write down. It's 1 minus lambda, this term, times this term, which I'm going to write as minus 1 plus lambda. And then I subtract from that this term times this term, I times minus I. And that's all going to be equal to 0. If you expand this out, you end up with minus 1 minus lambda squared from these two terms, minus 1 from this equals 0. So the actual equation you have to solve in this case is pretty easy. Lambda squared equals 2. What that means is that our eigenvalues, lambda, are equal to plus or minus the square root of 2. So we have two eigenvalues, plus and minus the square root of 2. So we found our eigenvalues. What about our eigenvectors? The best way in general to solve for the eigenvectors is to go back to this equation, substitute in the value of the eigenvalue, and solve the system of linear equations that results. So let's see what happens when we do that. Given this is our original matrix, let's suppose we have just the eigenvalue root 2. Let's just work with finding the eigenvector associated with the eigenvalue square root of 2. Our linear system, as before, A times some vector A equals lambda times A, can be reduced to A minus lambda times the identity matrix times A equals to 0. So let's just write our system like this. We have our matrix A minus lambda, which we now know is the square root of 2. So when I substitute that in here, I get 1 minus the square root of 2 for my upper left element, minus I, unchanged, for my upper right element, I for my lower left element, again unchanged, and minus 1 minus the square root of 2 for my lower right element. This is my matrix, and it will be multiplied by some unknowns, say x and y. So I can expand out this matrix vector product and get a system of equations that I can solve. For the first equation, I get 1 minus the square root of 2 multiplied by x minus I y equals 0. For the second equation, I get I times x minus 1 plus the square root of 2 y equals 0. And if, for instance, I rearrange this equation, which tells me that x is equal to minus 1 plus the square root of 2 y, and, sorry, minus I times 1 plus the square root of 2 y, and substitute this into this equation for x, what I end up with, and I'm writing it in the margins because you'll see this doesn't actually work, I end up with minus 1 minus the square root of 2 times 1 plus the square root of 2 times I y minus I y equals 0. And if you expand all this out, you find 0 equals 0. Effectively, I get Iy minus Iy equals 0. So it didn't actually tell me anything, but we knew that was going to happen because we set lambda such that the determinant of this matrix was 0. So this system of equations does not uniquely determine a solution. It does actually determine the direction. Essentially, these represent two parallel lines that are overlapping on top of each other, and the direction of those lines is interesting. And the easiest way to figure out what the eigenvectors is, then, is just to take one of these equations and substitute 1 in for x. And if you do that, you can just write down the vector more or less. You find that the vector is 1, and then solving a single one of these equations, substituting in 1 for x, you can see you're going to get something like minus Iy, and then in the denominator you're going to get 1 minus root 2, and then in the denominator you're going to get minus I. You end up with I, say, root 2 minus 1. That's actually your eigenvector associated with the eigenvalue square root of 2 for lambda. If you repeat this procedure with lambda equals minus the square root of 2, our other eigenvalue, you get more or less the same sort of structure. Again, an algebraic system of equations that cannot be solved. It just ends up looking slightly different. And you have 1, and then minus I, 1 plus square root of 2. Sorry for writing so small here. But the overall procedure for finding eigenvectors, at least by hand, for small matrices like this, it is most easy to substitute in the eigenvalue that you found by solving the characteristic equation, setting the determinant for this matrix equal to 0 and solving for lambda, then getting a system of equations that is singular, and doing your best to solve the singular system of equations, substituting in a variable as needed. Given this discussion of eigenvalues and eigenvectors, it's useful to consider the concept of diagonalization. The eigenvalues have this special property where they are mapped back to themselves by your transformation. And it turns out that we can use these eigenvalues and eigenvectors to make a change of basis that converts your matrix into a diagonal matrix. This process is called diagonalization. To see how this can happen, consider I have some transformation A. I can express A in any basis, really, and I'll consider two bases, just any old basis, and then an eigenvector basis, where I mean finding the eigenvectors of the transformation A and using those eigenvectors as basis vectors. If I express the matrix, or the transformation A in any old basis, I'll just call that the matrix A, whereas in the eigenvector basis, I'll call that matrix A prime. Let's think about what A prime does. A prime, as any representation of this transformation will do, it will take an eigenvector alpha, and, sorry, I should write these as vectors, not kets. This transformation A prime will take a vector A and return lambda multiplied by the same vector, a scaled version of the original vector. If I consider what A prime actually looks like, and what A actually looks like, this eigenvalue equation will only be solved, suppose, say, I have A1 and eigenvalue 1, where lambda 1 is the eigenvalue, the first eigenvalue, and A1 is the associated eigenvector. In the eigenvalue basis, which is where we're expressing A prime, I'll just leave A prime blank for now. What does our eigenvector look like? Well, we're expressing an eigenvector in the eigenvector basis. So the eigenvector basis, if this is, say, two components, lambda 1 and lambda 2, lambda 1 and eigenvector 1 would constitute the first component. So I'll have some number here. I'll just call it, well, I'll just say 1. whereas the component in the direction of the other eigenvector would be 0. We just have a single eigenvector here, and we have no contribution from any other eigenvectors. If I act with a prime on this, I have to get lambda times our original vector back. This also has to hold if I, again leaving a blank, use the other eigenvector. I have to get the same sort of equation, 0 lambda, where this now, let's say this is lambda 1 and this is lambda 2. First eigenvector, second eigenvector. So my first eigenvector, written in the eigenvector basis, is very simple. My second eigenvector, written in the eigenvector basis, is simple as well. And the matrix that works here has lambda 1 and lambda 2 on the diagonal, and zeros off the diagonal. Lambda 1, 0, 0, lambda 2. And you can see that this matrix works pretty well. And this matrix has the nice property that it's diagonal. It's much easier to work with diagonal matrices than non-diagonal matrices. So what we're looking for now, knowing that A prime is diagonal, if I express my transformation in an eigenvector basis, I need to make a change of basis. Typically, you won't be given a transformation, you'll be given something like a matrix, and it won't be written in the right basis. So you need to make a change of basis. So we're looking for some change of basis that gives me A prime in terms of something, and I'll write it as S inverse times the original matrix that you're given times S. If you consider this acting on a vector in the eigenvector basis now, what S has to do is convert from the eigenvector basis to the basis of our original matrix A. So if I have a transformation that goes from my eigenvector basis to the basis of A, I can actually just straight write down that basis. And write down that transformation, that matrix. And what it looks like is your first eigenvector as a row, and then your second eigenvector as a row. This is now going to take your first eigenvector, for instance, if I write it as 1, 0, or 1, 0, like this, and what it's going to give you is v1 as a vector. So you have your vector v1. That's your result. It does the same sort of thing for v2. So this takes components expressed in your eigenvector basis and expresses them as the eigenvectors themselves. This is exactly what we want our change of basis matrix to look like. So if I make this matrix, this is my matrix S. A matrix constructed with rows given by the eigenvectors of your original matrix A. So we can take a matrix A in any basis, provided it has the right properties, find the eigenvalues, find the associated eigenvectors, and construct the matrix S, which, when multiplied by A in this format, will go from your eigenvector basis to the basis of A, allow A to act, and then convert back to the eigenvector basis. And we know that that has to have this diagonal form. So A prime is equal to S inverse A S, where S is given here, and it has this form, lambda 1, lambda 2, dot, 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 up to lambda n, with zeros off diagonal. So we have our eigenvalues along the diagonal, and we have zeros off diagonal. This is the process of diagonalization, and it will end up being a major component of quantum mechanics, since the process of finding the eigenvalues and the eigenvectors is associated, and we'll talk more about this later, is associated with the process of finding the stationary states of the Hamiltonian, for instance, if the transformation we're considering is a Hamiltonian. We'll of course talk more about that in detail, but for now, the last topic is Hermitian transformations. Hermitian transformations have a lot of nice properties which can only really be expressed in terms of the eigenvalues and the eigenvectors, which is why I put off their discussion until after we had discussed eigenvectors and eigenvalues. But to recall, a Hermitian transformation, we described it in terms of matrices. A Hermitian matrix is a matrix such that the Hermitian conjugate of the matrix, which is equal to the complex conjugate, transpose and complex conjugate of the matrix, is equal to the original matrix. There's another way of defining this, and in terms of transformations, the best way to think about this is as an inner product. Suppose I have some vector alpha, and I'm going to take the inner product of that vector with the product of what I get when I apply some transformation A to a vector beta. If a transformation is Hermitian, we have that this is equal to a hat acting on alpha inner product with beta. Sorry, this is not just a hat. This is the Hermitian conjugate of a hat. So if we allow our transformation to act on the vector on the right of the inner product, versus we take the Hermitian conjugate of the vector a, or the transformation a hat, and allow it to act on the vector on the left of the inner product. This is the essence of taking the Hermitian conjugate of a vector. If we take this transformation and allow it to act on the right, we could equivalently take the Hermitian conjugate and allow the operator, the transformation, to act on the left. So in terms of matrices, you can think about this sort of inner product, which is really poor notation because this a hat beta ket is not necessarily meaningful. You have to think about a hat, the transformation, acting on the vector beta. But what this actually ends up looking like in terms of matrices, if we express something in a basis, we have the bra alpha, which let's just write that as a dagger. And then we have some matrix, and I'll use capital A, representing our transformation, a hat. And then that's going to act on the vector B, which is taking the place of beta here. I can equally well express this as the Hermitian conjugate of the matrix, which I keep writing as T, the matrix A, acting on the vector A, and that acting on B. So that's essentially equivalent to this notation. Taking the Hermitian conjugate of a matrix and letting it act on the left is essentially taking the Hermitian conjugate in this context. So what this actually looks like, the Hermitian conjugate now of a vector is, well, it's a complex conjugate transpose. So instead of having a column vector here, we have a row vector. Our matrix A is a matrix, as always, and B, not being Hermitian conjugated, is a column vector. When I take the Hermitian conjugate here, you can think about this as being your matrix, which is now Hermitian conjugated, acting on the vector A now, and then when we're done with that, we allow it to act on B. So I can take this sort of matrix vector product, and I can take this sort of matrix vector product, and everything is okay. So an operator is considered to be Hermitian if a dagger in the matrix context is equal to A, or equivalently if it doesn't matter if I allow this transformation to act to the right or to the left. It's a very useful property to have, and Hermitian properties have some, or Hermitian transformations have some really nice properties. If we have a Hermitian matrix, or a Hermitian transformation, or a Hermitian operator, depending on whatever terminology you choose, the eigenvalues of this matrix are real. And you can see that by looking at the expression, say I have some vector alpha, and I will then use Hermitian operator T acting on alpha as well. This, you know what T does to alpha. If we have the state, if alpha is an eigenstate, we have this sort of expression. So I know what T does to alpha. It gives me lambda times alpha. But if this is Hermitian, I can of course pull the lambda out and get the inner product of alpha with itself. If T is Hermitian, I can also allow this to act from the left, like so. These would then be equal to each other. And, well, again, you know what T does to alpha. It gives you lambda times alpha. But now we have lambda left multiplying something. And on the left here, we're dealing with a Hermitian conjugate of our vector. So essentially we have to complex conjugate lambda. So we'll end up with lambda star, and then alpha inner product with alpha. So if these two are going to be equal to each other, lambda equals lambda star, we know the eigenvalues of this transformation are real. The next key fact about Hermitian transformations is that the eigenvectors from distinct eigenvalues are orthogonal. And you can see that by much the same sort of reasoning we applied up here. Consider some eigenvector alpha, inner product with some Hermitian transformation acting on some other eigenvector beta. If I allow t to act on beta, I will get the eigenvalue associated with the eigenvector beta, alpha, and I'll call that mu. So this is going to get me mu times alpha inner product with beta. If t is Hermitian, I can just as easily as before allow t to act on alpha, t hat alpha from the left. And when I allow t to act on alpha, I end up with the eigenvalue associated with alpha, which I'll call lambda. So we'll end up with lambda alpha inner product with beta. As before, I can pull out the lambda here, but since I'm now on the left with the bra instead of the ket, with the Hermitian conjugate instead of the vector itself, I end up with the complex conjugate of lambda times alpha inner product with beta. If these two things are going to be equal to each other, and mu not equals to lambda, or mu not equal to lambda star, this can only be true, this can only happen if alpha inner product with beta is equal to 0. This is really nice because this tells you that the eigenvectors are orthogonal. And if you're thinking ahead, you think orthogonality is a really good property for basis vectors to have. And if you have an orthogonal basis of eigenvectors, then your transformation has a really nice form as well. The final property is that the eigenvectors span the space. And this is sort of true, but there's some caveats. Unfortunately, or fortunately, sorry, the caveats are not really all that important for quantum mechanics. If you have a transformation with n eigenvalues, and they are n distinct eigenvalues, you're guaranteed that the n distinct eigenvectors will span the space. Since if I have a space of dimension n, my matrix that is expressed in some betas, the matrix representation of my transformation will have n eigenvalues, and I will get n distinct orthogonal vectors. And the only way you can have n orthogonal vectors in an n-dimensional space is if they span the space. So those are some of the nice properties of Hermitian operators. This was a lightning-quick review, hopefully, of linear algebra. We will work with some of these concepts in more detail later. But for now, to check your understanding, here is another matrix, different from the one that I worked with. It's also 2 by 2, so these calculations are not terribly difficult. Your task is to find an eigenvalue and its associated eigenvector. Since this is a 2 by 2 matrix, and if you look, this matrix is also Hermitian, you know it's going to have 2 real eigenvalues, and the eigenvectors should be orthogonal, and you can go ahead and check those properties as well. But for now, just find an eigenvalue and its associated eigenvector. We'll be doing this sort of thing in the context of quantum mechanics, even with systems as simple as two-state systems where you have 2 by 2 matrices later. The mathematics of quantum mechanics is, technically speaking, linear algebra in an infinite dimensional vector space. Now, if that seems a little bit unfamiliar, don't worry, we will work through it step by step. It does turn out, however, to be an immensely powerful mathematical structure. There's a lot more going on behind the scenes to quantum mechanics than simply the wave function. What we're really talking about, in terms of the formalism of quantum mechanics, is attempting to represent the quantum mechanical state of the system. Now, what is the state of the system? Well, quantum mechanically speaking, it's everything that we can possibly know about the physical system that we're working with. There is no further level of information than knowledge of the state. And we've been working with states in a couple of different ways. The first way we worked with state was this notion of a wave function, let's say psi of x and t. And to some extent you can write down sort of closed form mathematical expressions for psi. Let's say psi is equal to some sort of, maybe it's a Gaussian, or a sinusoid, or a complex exponential. We also thought about representing the state of the system as a superposition, a sum over n of some coefficient a sub n, multiplied by some psi sub n of x and t, where these psi sub n's come from solutions to the time-independent Schrödinger equation. We're talking about, say, particle in a box, or the quantum harmonic oscillator. Gives you sets of wave functions that you can superpose together to represent an arbitrary state of a quantum mechanical system. We also talked about representing the wave function as some sort of an integral. Perhaps we're integrating from minus infinity to infinity. Instead of summing, we're computing an integral. We're integrating perhaps decay, if we're working with the free particle, for instance. And we have some sort of a phi of k, some sort of a coefficient that tells you how much each of the stationary states for the free particle that we have to work with. And those free particle states look something like e to the I kx minus h bar k squared over 2m t. And there was a normalization divided by the square root of 2 pi, if I recall correctly. Now these expressions bear a certain similarity. Instead of a sum, we have an integral. Instead of a discrete list of coefficients, we have a function, phi of k. And instead of a stationary state, we have a stationary state. We also talked above and beyond these sorts of representations, hinting at some sort of a deeper mathematical structure. We wrote down expressions like psi sub n is equal to a plus the operator acting on psi sub n minus 1, all divided by the square root of n. This sort of expression came from a consideration of an operator algebra that actually had no knowledge whatsoever of the states. So while you can think of representing the states as sort of a closed-form mathematical function, some sort of a list of coefficients, some sort of a function, there's actually more going on behind the scenes. We also have this notion of operators relating different states to each other, and these expressions are going to be true regardless of the nature of psi 1 or psi n and psi n minus 1. That expression has to hold. Why? Well, there is a deep mathematical structure going on behind the scenes here. So let's explore that mathematical structure. That's what this chapter is all about. So, what we're working with here, like I said at the beginning, technically speaking, is linear algebra in Hilbert space. Now, if you've studied linear algebra, you know it deals a lot with vectors, and you can gain a lot of intuition about the behavior of physical systems in terms of vectors. So, say we have some sort of a vector A pointing in that direction, some sort of a vector B pointing in that direction. You can do basic vector operations on these things. We can, for instance, take the dot product of A and B. And I've drawn these things as approximately perpendicular to each other, so you would expect the dot product to maybe be 0. We can also write perhaps the vector B as some sort of linear transformation acting on a vector A. And in the language of three-dimensional vectors, it's easy to write down linear transformations as matrices, in this case 3 by 3 matrices. So if you've studied linear algebra, these sorts of concepts are familiar to you. In particular, there are a lot of linear algebra concepts, things like the inner product or normalization or orthogonality and the notion of a basis that we can express. Now, the nuance in quantum mechanics is that we're working with a Hilbert space. And a Hilbert space, technically speaking, is an infinite dimensional vector space. So the infinite dimensionality here, I think I've actually written infinite, but you get the idea. Instead of working in 3 dimensions, we're working in infinite dimensions. Instead of lists of 3 numbers, we need lists of infinitely many numbers. And that makes life a little bit more difficult. The basic structure ends up being the same, though, so much of your linear algebra experience is still going to hold here. To give you some basic vocabulary and some basic intuition, we're dealing with vectors, first of all. And the notation that we'll use for a vector in the notion of a vectors in this Hilbert space is going to be something like this. So, vertical bar, name of vector, and then angle bracket. We'll expand on this notation much more later on in the chapter, but for now, just think of this vector as somehow representing the state of the system. As a proxy, think something like psi of x, if you need a more concrete representation of the state. You don't want to just think in general. Now, I contend that when we're talking about linear algebra and Hilbert space as applied to quantum mechanics, this representation is actually more useful than the wave function, and we'll see why that's the case later on. Oftentimes, we don't need to know anything about the wave function to still make useful conclusions on the basis of the vectors themselves. So what else can we do in terms of linear algebra? Well, we can do inner products. The way we'll write that in this notation is BA, or beta alpha here, angle bracket, beta, vertical bar, alpha, angle bracket. In the language of states and wave functions, you can represent inner products like this as integrals, minus infinity to infinity, of, in this case, let's say psi beta star as a function of x times psi alpha of x, all integrated to dx. This is that same sort of normalization and orthogonality integral that we've been dealing with a lot in the context of wave functions, but expressed in a more compact notation, in a more general mathematical form, that of linear algebra. with this notion for an inner product, we can also think about normalization. Something like the vector alpha inner product with the vector alpha would translate into wave function language as an integral from minus infinity to infinity of psi sub alpha of x, psi sub alpha of x, need to complex conjugate this one, sorry about that, dx. And in terms of normalization, this had better equal 1, and this had better equal 1. So the inner product of a vector in this Hilbert space with itself had better give you 1 if this is going to represent a valid quantum mechanical state, same as the wave function has to integrate in this squared modulus context to give you 1. We can also talk about orthogonality. Orthogonality, in the language of linear algebra, refers to the vectors being perpendicular to each other, if you're just thinking in 3 dimensions. Now, in infinite dimensions, it's a little bit harder to express, a little bit harder to think about, but it's just as easy to write down. I can say alpha and beta equals 0. That means these vectors are orthogonal to each other. In the language of integrals here, integral from minus infinity to infinity of psi alpha of x, complex conjugate, psi beta of x is going to give you 0. If these come from, for instance, a solution to the time-independent Schrödinger equation, perhaps we have a set of wave functions to work with. I'll write that as a set of states, say psi sub n. I may be guaranteed that psi sub n inner product with psi sub m gives me a Kronecker delta. This would express orthonormality, that this set is every element in this set is orthogonal with every other element, and that each element of the set is properly normalized. We can also talk about the completeness of a basis. So working with this sort of set psi n, suppose it comes from solving the Schrödinger equation in the language of the wave function, I can express some arbitrary psi, arbitrary quantum mechanical state, as a sum of, let's say, n equals 1 to infinity potentially, of a sub n, psi sub n. If this sort of expression is possible, these psi sub n's form a complete basis. And if you think about invoking the orthogonality and applying Fourier's trick to this sort of expression, that works out just as well. You can figure out that in this case a sub n is going to be what you get if you take the inner product of psi sub n with this arbitrary wave function that we're starting with. Now these expressions have corresponding versions in terms of the wave function as well, but since I'm running out of space on the slide, I'm not going to go into the details. This one is going to be an inner product, same sort of integral as we're working with here. Likewise, this is your infinite sum. I think I had that expression on the last slide. Now, within the language of linear algebra and Hilbert space, we have this sort of notation, these sorts of representations for what these states really are as they exist in the vector space, or in the Hilbert space. What can we do with these states? Well, the fundamental question in quantum mechanics generally has to do with the observable properties of a system. So what do we have in the language of observables? Well, observables, we know, are going to be real numbers, and they have some sort of statistical properties in quantum mechanics. For instance, we talked about the expectation value. Say I have some sort of observable Q, I can write the expectation value as Q inside a pair of angle brackets. And the angle brackets here are not exactly the same as the angle brackets in the earlier expressions that we've been working with, but the connection is, there is a connection. We'll come back to that later. If you want to think about the expectation value, for example, in terms of some sort of quantum mechanical system, we're dealing with an operator. So the observable isn't just going to be the expectation value of some Q, some quantity Q. We've got some sort of an operator, which I'll write as capital Q with a hat. So what would our expectation value Q look like in this language of angle brackets? Well, we know what it looks like in terms of inner products, or in terms of integrals of wave functions, for example. It's going to be an integral of the wave function, the state of the system, then the operator, then the wave function of the state of the system. And we have that same sort of notation in context of inner products in our vector space. So we would have the state of our system, psi, and we have our operator acting on psi. So the operator acting on psi gives you, in some sense, another state of the system. It's not really another state of the system, though. It's more a vector in this Hilbert space. Operators here, if I think about this Q operator acting on the state of the system, is going to give you some new vector in your Hilbert space. Now, we know that this sort of expectation value quantity or concept has to result in some sort of a real number. So you can think about this as, what happens if I take the complex conjugate of this? Well, if you're thinking about psi, q hat psi, complex conjugated, in the language of the integrals that we've been working with, this is going to be taking the complex conjugate of q hat psi. So instead of being a psi star q hat psi, it's going to be a q hat psi star multiplied by psi inside the integral. And the same notation sort of holds here. Whenever you take the complex conjugate of an inner product like this in our Hilbert space, you swap the order of these things. Instead of the psi being on the left, the psi is on the right. And the q hat psi on the right is on the left. So this notion of what appears on the left and what appears on the right is a useful way of keeping track of what's been complex conjugated. So q hat psi psi in our revised notation here. Now, this sort of substitution here, if this is going to be equal to the original expectation value of q, right? The complex conjugate of the expectation value has to be equal to the expectation value itself if this is going to be a real number. This expression has to be equal to this expression. And the equality of two operator expressions in the language of linear algebra like this, essentially the operator can act on the left or the operator can act on the right. The operator behaves the same when acting on a complex conjugate of the state as it does on the state itself. Complex conjugate of state with operator gives you the same result. That is only going to be true if the operator here is Hermitian. And there's lots more that can be said about the notion of Hermitian operators, and we'll come back to that in further lectures. But for now, know that there's a lot of mathematical formalism that goes along with linear transformations, such as vectors to new vectors in the space, especially associated with Hermitian linear transformations. So as an example of the notion of a Hermitian operator and how that manifests itself in this context, think about the momentum operator. Is the momentum operator Hermitian? Well, if the momentum operator is Hermitian, we know that if I have some sort of a wave function f, the momentum operator acting on the wave function g has to be equal to the momentum operator acting on f, inner product with the wave function g. Sorry, I shouldn't say wave function, I should say state. State f, momentum operator g, momentum operator f, state g. These things should be equal to each other. So let's do some manipulations of the one on the left. And just since we have a large amount of machinery for working with the notion of states in terms of wave functions, let's express this in terms of wave functions. So our inner product in the terms of the wave functions is going to be the integral from minus infinity to infinity of some wave function f, complex conjugated as a function of x, multiplied by the momentum operator applied to our wave function g. And our momentum operator is minus I h bar, partial derivative with respect to x. So this is acting on the function g of x, and we're integrating dx. Now this is an expression that looks a little bit difficult to work with. We have partial derivatives inside an integral, but whenever you see a derivative inside an integral, think integration by parts. So let's say I do integration by parts. I can define my variable u to be some sort of f complex conjugate, recognizing the part that I would like to differentiate. And the part that I would like to integrate would be, well, the part that's already been differentiated. So let's say dv is equal to partial g partial x with the dx tacked on. So identifying this part as my v and this part as my u. And you can pull the constants out front if you want. So this is going to give me du would be the partial derivative of f star partial x, and my v when I integrate it, now it's the integral of a derivative, so fundamental theorem of calculus just gives me g. Integration by parts then says this whole thing is going to be equal to f of x, f star of x g of x evaluated at my boundary, minus infinity to infinity, minus the integral from minus infinity to infinity of these two guys, v du. So I have my partial f, partial x, and I have my g, and I'm integrating dx. Oops, forgot to, technically I should put a dx there in my integration by parts notation. So, as usual in quantum mechanics, we require these functions to be square integrable, meaning normalizable, meaning they have to go to 0 at infinity. So 0 at plus infinity, 0 at minus infinity, this term all by itself drops out. Oh, and I've got this coefficient overall that I should pull out front. So minus I h bar multiplies all of this. So I've got a minus I h bar and a minus. The minus I h bar and the minus are going to cancel out if you want to simplify this, and I'll have I h bar. Let me put that inside the integral. I h bar, I have a partial derivative of f star, partial x, and g, and I'm integrating dx. So we're almost there. This looks a lot like the momentum operator applied to the function f. So we've almost sort of closed the loop here. We've almost shown that p is Hermitian. What's missing here? Well, what's missing is the notion of this minus sign on the IH bar. This here itself is not exactly the momentum operator applied to f. But what we want actually isn't exactly the momentum operator applied to f. It's the momentum operator applied to f, but then acting on the left in this inner product notation, which means we have to take the complex conjugate. So if I really wanted to write this out, I would have to say this is the integral, put some limits on here, minus infinity to infinity of minus I h bar partial f partial x, all complex conjugated, multiplied by g integrated to dx. And now we've actually gotten back to this original expression. This here is the operator p acting on f, complex conjugated, inner product with the function g. So that's the end result. We have sort of demonstrated that our definition of minus I h bar partial g partial x here is indeed a Hermitian operator. And perhaps this goes a little bit of the way towards explaining why exactly you had a minus I h bar, or minus I, in the definition of the momentum operator. That minus I is a little bit perplexing at first, but it is required essentially by the notion that the momentum operator be Hermitian, by the notion that the expectation value of the momentum is always going to be a real number. As a further example of how we can manipulate these sorts of things in the language of formal linear algebra, let's think about a state with no uncertainty. What sort of quantum mechanical state would have no uncertainty? These things are also called determinate states, meaning you have some operator or some observable, let's say the observable q as represented by the operator q hat, and it has absolutely no uncertainty associated with it. There is a quantum mechanical state that has a definite value of some variable, some observable. Now, if you're thinking about something like position or momentum, you might be thinking along the lines of the uncertainty principle, and well, is that really possible? And the answer is probably not. The states of determinate position and determinate momentum tend to be a little bit poorly behaved, mathematically speaking. But in terms of energy, perhaps, you know states of determinate energy. They are the solutions to the time-independent Schrödinger equation. So there's certainly nothing wrong with that. In particular, I can write something like sigma q, the variance, sigma q squared, the uncertainty in a measurement of quantity q squared. And I can write that this quantity was, back when we were talking about variance and probability distributions, defined as the expectation value of the operator q minus the expectation of q. So the deviation of some observable from its mean squared. So the expected mean squared deviation, the mean squared deviation from the expected value. Now, in our language of linear algebra here, we can write this out as psi on the left, and then q hat minus the expected value of q acting on psi on the right. Oh, and this is squared, of course. So I can expand out the square, let's say psi on the left, and then q hat minus expected value of q hat minus expected value of q twice, acting on psi. And this operator, if this is going to represent an observable, has to be Hermitian. So if q hat, the operator, is Hermitian, q, multiplication by a number here, the expected value of q, this is just going to be a number. It's also, of course, going to be Hermitian. Multiplication by a number is going to be a Hermitian operator. Doesn't matter if you do it on the wave function on the right or the wave function on the left. I can take this whole thing and apply it on the left, since this is a Hermitian operator. So if you make that sort of manipulation, you end up with, now on the left, I have q hat minus expectation of q acting on psi, and on the right, q hat minus expectation of q acting on psi. And if this whole thing is going to have zero uncertainty, what exactly does that mean? Well, if this whole inner product is going to turn out to be zero, then either psi equals zero, meaning my wave function is in some sense trivial. That's not terribly useful. If psi is not zero, then each individual piece here, this has to in some sense be equal to zero. Or this piece on the left has to be equal to zero. What that means, well, either left and right, these are very similar expressions. It means q hat minus the expected value of q. In terms of that as an operator acting on my state, that has to equal zero. And that's easily rearranged into q hat acting on the state equals the expected value of q multiplied by the state. This is just a number, it's not an operator. This here, this is an eigenvalue problem. And there is yet another massive set of linear algebra machinery dedicated to solving eigenvalue problems. We've already done some of them. For example, the Hamiltonian operator acting on the state of the system is the energy times the state of the system. This is our time-independent Schrödinger equation. This gave us the states of definite energies, and that's the same sort of framework as you got in here. So that's a taste of the sorts of things that we can represent and think about in the language of linear algebra as applied to quantum mechanics. We can express generalized states with no uncertainty and derive that they are going to be the states that are eigenstates of the linear operators that represent the observables. Now, we haven't really written down any linear operators in detail in the notation of linear algebra or really in quantum mechanics. We've only really got a few operators that we can work with, like Hamiltonian and position and momentum and whatnot. But this is hopefully I have at least convinced you that there's more to quantum mechanics than just dealing with the wave function, that we can do some interesting things with the linear algebra structure. So, to check your understanding here, let's consider a set of states that you get, stationary states from the quantum harmonic oscillator. That means the solutions to the time-independent Schrödinger equation, which if you wanted to write it out in terms of operators and linear algebra, is h bar psi sub I, let's say psi n actually, is equal to En psi n. So that would give us this set of solutions here. So in terms of the language of linear algebra, some basic notational questions. And in terms of whether or not observable operators are Hermitian or not, think about why the operator x hat, the position operator, would be Hermitian. Let's continue our discussion of the mathematical formalism of quantum mechanics by considering Hermitian operators and the eigenvalue and eigenvector problems that result from their consideration. What we're talking about here is a Hermitian operator in general. So for a Hermitian operator, I'll just write q with some hat on it. And you can consider just this general operator to be Hermitian if the following condition holds. The inner product of some arbitrary function, arbitrary state in the Hilbert space, f, inner product with the operator acting on some arbitrary state in the Hilbert space, g, is going to be equal to the operator acting on the state f, inner product with the state g. So if this inner product and this inner product are equal to each other for all f and g, then the operator is Hermitian. These sorts of operators show up a lot in quantum mechanics because Hermitian operators are what we are considering if we're talking about observable quantities in quantum mechanics. Now, in terms of eigenvalue problems, the general statement of an eigenvalue problem looks like the operator applied to some general state is equal to some eigenvalue, which I'll write as lowercase q, in the case of the operator uppercase q, multiplied by that state. So applying the operator to the state doesn't really do anything. It only changes the overall scaling factor by some amount q. So these sorts of eigenvalue problems show up in quantum mechanics all over the time, or all over the place. For example, the time-independent Schrödinger equation is such an equation. We have the Hamiltonian operator acting on a state, giving you the energy multiplying the state. H psi equals E psi. Now, solving the eigenvalue problem gives you one of two general kinds of solution. First of all, what we're going to get are going to be eigenstates. Those are going to be our psi's that solve this sort of equation. Generally, we're going to get a lot of them. And we'll get some sort of eigenvalues. Those are going to be the values of q that result from application of this operator to a particular solution to the eigenvalue problem. And we're going to get many q's as well. Each solution to this problem, and there will be many, generally has its own distinct value of q in this sort of expression. And the sets of psi's and the sets of q's that solve these problems generally come in two discrete classes. We have discrete and we have continuous. The discrete case means that we have some explicit set of, let's say, psi sub n. There are a potentially infinite number of these psi sub n's, but we can write them down in a list. Psi 1, psi 2, psi 3, etc. We're also going to get some set of q sub n's, where q sub n goes with psi sub n. As an example of where this has occurred already that you've seen, talking about the particle in a box, solving the time-independent Schrödinger equation gave us a set of stationary states and the associated energies. For the continuous case, things are a little bit more complicated. For an example of this that you've seen before, consider something like the momentum operator applied to the wave function, giving you the momentum, the value, multiplied by the wave function. This sort of eigenvalue expression came up in our consideration of the free particle. And under those circumstances, we didn't get a real nice set of solutions. We got wave functions that looked something like, well, there was some free parameter k. And our wave function as a function of x looked something like a complex exponential. We had e to the I kx minus h bar k squared over 2m t for the time dependence. Probably we were dividing this by root 2 pi, if I remember correctly, to effectively normalize it within the language of the Fourier transform, at least. So there's no way of writing down psi 1, psi 2, psi 3, psi 4. There is only psi k, and k can take on essentially any value. The eigenvalue that we got was, well, in the case of the momentum operator, h bar k. Given the definition of k that we came up with in this consideration of the free particle, we have an infinite set of continuously variable solutions. This k value can be anything, as opposed to indexed by just an integer 1, 2, or 3 sort of setup. Now, the mathematics that results from a discrete spectrum, a discrete set of eigenvalues, versus a continuous spectrum, a continuous set of eigenvalues, are going to be a little bit different. But it's a little easier to understand the discrete case. It's a lot easier to write down mathematical expressions, so let's consider that case first. Most of the results will still hold, and we'll come back to the continuous case later on in lecture. So, the first thing that you probably want to know about the eigenvalues that result from these eigenvalue problems is whether or not they can possibly represent observables. And in this case, the eigenvalues of Hermitian operators are real. You can see that by fairly straightforward application of the eigenvalue equation itself, looking at q hat, the operator, applied to some arbitrary wave function psi, giving you the eigenvalue q, multiplied by the wave function psi. You can take the complex conjugate of that expression, and complex conjugating the left-hand side merely converts this into, well, the result of complex conjugating the operator acting on the wave, or acting on the state, which we're writing in our vector notation as angle bracket on the left instead of angle bracket on the right. Complex conjugating the right-hand side of this expression gives you, well, the complex conjugate of the eigenvalue, q star, multiplied by the result of complex conjugating this wave function, or this state, psi. So again, angle bracket on the left. The other ingredient to understanding why the eigenvalues of Hermitian operators are real is the definition of a Hermitian operator, which says that q acting on some state f inner product with the same state f, perhaps, is going to give you the same result as if you take the inner product of the state f itself with the operator acting on the state f on the right. Operator on the left, operator on the right gives you the same result. Now, if I apply this sort of expression over here, and this sort of expression over here, you can see what's going to happen. Applying the operator on the left turns this into q complex conjugate f, inner product with f, and applying this expression on the right turns this part into q, the number, multiplying f. Now, a number inside an inner product like this is just going to factor out, so we're left with q, the number, times f, inner product with f. And the inner product of a state with itself is always going to be non-zero. So I can effectively divide both sides of the equation by this, and thereby show that q star is equal to q. Therefore, our eigenvalues of the eigenvalue problem for a Hermitian operator is going to be a real number. Real numbers means that these are potentially feasible representations of observable quantities. So that's a step in the right direction. Now, we talked about a lot of other facets of solutions for the time-independent Schrödinger equation, for example. What about orthogonality and normalization and whatnot? We can talk about those within the language of eigenvectors and eigenvalues, eigenstates of a Hermitian operator. It turns out the eigenstates of a Hermitian operator are orthogonal to each other. Now, that's not a completely rigorous mathematical statement. I'll point out some of the difficulties with it later on. But in the context of orthogonality, we're talking about an inner product of two different states. So suppose I have q hat, and I'll say the state f gives me some eigenvalue qf, multiplying the state. And then I have a distinct state q, let's call it g, gives me the eigenvalue, not g, sorry, qg, multiplying the state g. These two eigenvalue problems are solved for the state f and for the state g. So in principle, I know f, I know g, or qf, I know g, I know qg. Now, if you consider the definition of a Hermitian operator in the context of the states f and g, I have f acting on q times g, and that has to be equal to q acting on f, inner product with g. This is our definition of a Hermitian operator. And we know, considering eigenvalues and our eigenvalue problems here, qg, I can write down that. That's just going to give me q sub g times the state g. So this is going to give me qg times the inner product of f and g. And qf on the left, we've talked about how to do that sort of thing on the last slide. This is just the complex conjugate of this sort of thing. So this is going to give me qf complex conjugated times the inner product of f and g. Now, this looks a lot like the sort of expression we were talking about before, but in the case of showing that the eigenvalues were purely real, we were working with the state f and itself, not the state f and some other state g. So, we have some potential problems with this expression. If qg and qf are not equal to each other, and f and g, the inner product here, is non-zero, then we have the same expression on both sides. It can be divided out. qg is equal to qf, but that's going to cause some problems. The problem that we run into is that we have a failure of our inequality here. And the inequality that fails if I say divide these things out, if qg is different than qf, then I have a contradiction. The contradiction is that f and g don't have non-zero inner product. If f and g has zero inner product, I can't just divide it out because I'm dividing both sides of my equation by zero. So what we can conclude from this expression is that either f g is equal to 0 or qg is equal to qf. And I'll just say qg is equal to qf. Since we've just shown that the eigenvalues are real, qf star is equal to qf. So we've shown that if the eigenvalues are different from each other, then the inner product can be, or must be 0. If the eigenvalues are the same, we are not guaranteed that the eigenstates, f and g, will be orthogonal to each other. In the case that qf equals qg, we describe the eigenvalue as degenerate, and we have to go through some extra procedures in order to ensure that we have a well-behaved set of eigenstates. In particular, what we want to do is something called Gram-Schmidt orthogonalization. And aside from having a lot of letters in it, orthogonalization is simply the process of taking these two states, f and g, and converting them into two new states, f prime and g prime, that are constructed as superpositions of f and g, such that they are actually orthogonal. I won't go into the details here, but it has to do essentially with finding the component of the vector f that is not orthogonal to the vector g and subtracting it off of the original vector f, so that I only have the part of f that is orthogonal to g left over when I've computed f prime. So that's a little bit about the eigenfunctions in terms of their orthogonality. The other thing that we needed to be able to compute meaningfully in quantum mechanics is completeness. We needed to represent states, arbitrary states, as superpositions of, for instance, stationary states, solutions to the time-independent Schrödinger equation for, say, the quantum harmonic oscillator. In the language of linear algebra, the mathematical formalism of quantum mechanics, that's an eigenvalue problem with the Hamiltonian operator. And it turns out that we have the same sort of mathematical formalism there. The eigenstates of Hermitian operators are indeed complete. And I can't really say much more here than just give you a definition. In terms of the completeness, we're talking about our eigenvalue problem as before, giving us a spectrum of eigenstates, let's say psi sub n, and the resulting set of eigenvalues. And it turns out that this is indeed a complete basis. Within the language of linear algebra, the set of vectors here spans the complete space that you're working with. And what that means is that any arbitrary state, let me call it f, can be written as a superposition, let's say n equals 1 to infinity here, of some coefficient n multiplying psi n. So I can express any vector in my vector space as a superposition of this set of vectors. It forms a complete basis that spans any desired function that you would be interested in. You can, given the orthogonality of these states, as shown in the last slide, apply Fourier's trick to this sort of expression and determine that this a sub n coefficient is fairly straightforward to calculate. You just multiply from the left by psi sub n, take the inner product with the state that you want to represent. Now, it's important to note that this sort of statement is not on as solid a mathematical footing as the earlier states regarding orthogonality. The completeness is often not easily proven. It is typically going to be something that we assume, and while in the case of consideration of the wave function, we can write down the time-independent Schrödinger equation as a partial differential equation and apply the language of Sturm-Liouville theory and apply the results of Sturm-Liouville theory, in particular to show that the results are complete, or that the set of solutions to the time-independent Schrödinger equation forms a complete set of basis functions. The same sorts of results are typically going to apply here. So while we can't always prove it, we are generally going to assume it, certainly at the level of mathematical sophistication of a course like this. So that's about it for the results. One thing I did want to say before we close here is that all of what I've been stating so far are for discrete spectra. So what about continuous spectra? What if, instead of getting a discrete set of eigenstates and eigenvalues, I get a continuous set of eigenstates and eigenvalues? The example I gave earlier was a consideration of the momentum operator as an eigenvalue problem. If I have some arbitrary function, apply the momentum operator, and get that same function back, the solutions that we got looked something like e to the I kx minus h bar k squared over 2mt. with eigenvalues that look like h bar k. Now, first problem. This is not normalizable. So within the language of linear algebra, writing down something, like if I call this psi sub k, in the language of linear algebra, writing down something like psi k, what exactly sense does that make? Can I really say this is normalized? Well, if I have two different values of k, let me say, express this in terms of momentum instead. So I'll write this as a psi sub p. If you consider, say, psi p1 inner product with psi p2, what does the orthogonality actually look like? Orthogonality or normalization? Well, if you write this out in the language that we know, that we've been working with so far, that of wave functions, this is going to be the integral from minus infinity to infinity of, well, this sort of expression. First of all, I've got psi sub p1 complex conjugated, so that's going to be e to the minus I k1x minus h bar k1 squared over 2mt multiplied by e to the plus I k2x minus h bar k2 squared over 2mt. This is all going to be integrated dx from minus infinity to infinity. So in the case that p1 equals p2, meaning this is really the same state, then the exponential argument here is the same, but has opposite signs. So I've got e to the plus something times e to the minus something, which is just going to give me 1. I'm going to get the integral of minus infinity from minus infinity to infinity of 1 dx. What now? That's going to be infinity, surely, right? It's not a very meaningful expression. And it's going to give me something very large. Now, what if, let me move this over a little bit to the left, what if I consider p1 not equal to p2 then? Well, in that case, my integral here is going to have some function of x. k1, k2 are going to be different. In the subtraction here that I get if I combine these two things, I'm going to get some function of x. It's going to be like the integral of minus infinity to infinity of e to the I something x. There's going to be other stuff up here as well. But I've got this sort of oscillatory behavior. You can think of this as cosine plus I sine, in other words. Now, as far as formally defining this mathematically, what this limit says, you've got an oscillatory function, you're integrating it all the way to infinity. It's not going to go to infinity, it's going to oscillate, right? And it's going to oscillate about 0. It's going to average out to 0. So in some sense, we can say this sort of goes to 0. And I should really put this in quotes so that I don't make my inner mathematician too angry. We do know, however, from working with these in the past, that these do form a complete basis. These sorts of things can be used to express any arbitrary initial conditions. We talked about that in the context of the free particle when we wrote expressions like that the wave function psi of x, say, can be written as an integral from minus infinity to infinity of dk, some coefficient, phi of k, multiplied by, say, e to the ikx. These sorts of expressions, this is like the inverse Fourier transform of psi sub k. So given some suitable definition of psi sub k, these e to the ikx, these sorts of functions can actually represent pretty much anything that you might want. Now, if we substitute in our definition for phi of k back from when we were talking about these sorts of things, it looks like this. It's the integral from minus infinity to infinity, dk, from before, and our phi of k was itself an integral from minus infinity to infinity. This time it was an integral dx, and it was, let's not leave it as an integral dx because I've got x in this expression as well. Let's use a dummy variable, my usual squiggle, xi. Integral dxi of psi of xi e to the minus I k xi. So this sort of expression, that was our definition of phi sub k. If I multiply this by e to the I kx, continuing my expression over here, you end up with something that makes a certain amount of sense. In particular, I can manipulate this. Let's consider exchanging the order of integration here and manipulating these such that my exponentials multiply together. You can think of this as the integral from minus infinity to infinity, dxi first, and then the integral from minus infinity to infinity dk, e to the I combining these two things together, I'm going to get something like kx minus kc. And all of this is going to be multiplied by psi of xi. Now, if this whole thing is going to be equal to psi of x, this expression right here should look familiar. What function gives me psi of x when multiplied by psi of a dummy variable and integrated over the dummy variable? This function here, this guy. We have a name for it. It's delta of x minus xi, or xi minus x. So this is sort of delta function. This is what I'm really going to get out of these sorts of normalization conditions. The infinity that it goes to when p1 equals p2 is like the infinity that the delta function goes to when x equals 0, or x minus xi, or x equals xi. The 0 that it goes to is like the 0 of the delta function when its argument is non-zero. So subject to this version of orthonormalization, that if p1 is not equal to p2, you get 0, and if p1 is equal to p2, you get, well, infinity, but infinity in a useful way, such that in the context of integration, I can get functions out that as I would expect. You can prove the same sorts of results for an eigenvalue problem with a continuous sort of spectrum. That's about all that I want to say about these sorts of topics. To check your understanding, let's consider the position operator x hat. Is it Hermitian? What is the spectrum like? Is it continuous or discrete? What are the eigenfunctions of x, the operator? And do those eigenfunctions form a complete basis? So think along those lines, and hopefully that will help solidify this notion of the mathematical formalism that we've been working with in the language of in the context, of Hermitian.